Consider a fluorescent bulb which is glowing. It is emitting light in all directions. So all these arrows represent various paths along which the light is traveling. These arrows are what we call the rays of light. Here's how we define a ray of light. A ray of light is a straight line path along which the light travels. The light emitted by luminous objects travel in variety of directions. Suppose rays of light from this fluorescent bulb fall on a surface, it being a non-luminous reflects these rays, and these reflected rays travel along a certain path. Consider this plane surface. Suppose one of the rays of light from the bulb strikes at this point. This is called as an incident ray. We know that this surface will reflect these rays and the reflected ray will travel in this direction. Why only in this direction? Why not here and here? This is because rays of light obey certain laws of reflection when they strike any surface. Draw a perpendicular to the surface at the point of incidence. This line is also called as normal. Here are the two laws of reflection that any light ray obeys. To understand the first one, we need to understand the angle of incidence and angle of reflection. The angle of incidence is the angle made by the incident ray with the normal. It is denoted by I. The angle of reflection is the angle made by the reflected ray with the normal and is denoted by R. So our first law is that the angle of incidence is always equal to the angle of reflection. That is, I is equal to R. This was about the first statement. What about the second statement? The second one tells us that incident ray, reflected ray and the normal all lie in the same plane. So if I draw this scenario on a piece of paper, I will get this. Incident ray, reflected ray and the normal, all three are in the plane of paper. For example, if the reflected ray is in this direction instead of this, then the diagram will look like this. The incident ray and the normal are in the plane of paper, whereas reflected ray is not in this plane. This violates our second law, hence the ray will not be reflected in that direction. This is just not possible. It can be only like this. I will be equal to R and they will lie in the same plane. These images formed by the concave mirrors have same characteristics as plane mirrors. You all must have seen the reflection of your face in the spoon. Spoon has smooth surfaces, one curved inside and the other curved outside. However, it's not perfectly spherical. For the ease of understanding, we can consider the reflecting surface which is curved inwards as a concave mirror. Now let's see how the image appears, but using an actual concave mirror. So let's try and find out the properties of an image formed by a concave mirror. We have to consider the front view and the side view. The side view is just to show the different positions where the object is kept, as it is difficult to do that in the front view. Let P be its pole, C be the center of curvature. The line joining them is the principal axis and F is the principal focus, also called as focal point. Assume that initially the object is kept close to the mirror. The table on the right with 3 columns telling us where the object is kept, the size of the image formed and the nature of the image. So initially the position of the object is between F and P. What does the size of the image look like? We see the reflection in the concave mirror and the image is bigger in size. We see that it is enlarged. So we say that when an object is kept between principal focus and pole, the image formed is enlarged. What about the nature of the image? Yes, it is a virtual image. It appears to be formed behind the mirror. Where is the location of this image? It's a virtual image, so it does not have any location. It only appears to be formed on the location behind the mirror. But we will find that location using ray diagrams. For now, let's move the object away from the mirror and see how the dimensions and the nature of the image are very relative to the object. You will find that as I move the object away, the image gets even bigger. And when the object is at principal focus, the image is huge. We say that when the object is at the principal focus, the image is highly enlarged. Is it a real or a virtual image? It's a real image. Since it's a real image, it's upside down. Or we use another word for it, which is inverted. It is formed on the same side of the mirror as the object is. And believe it or not, the image is actually formed infinitely far away. When I start moving this object away from the focal point towards C, the image is still enlarged, but the size is reducing. And what about the nature of this image? Yes, here the image is upside down. The real image is when object is at the point C. At this point, both the object and the image are of the same size. If I move this object beyond point C, the image remains real and inverted. But now, the size of the image is actually smaller compared to the size of the object. So we say that the image is diminished. This is also a real image. As we keep moving the object beyond C, the size of the image keeps reducing. Let us study the uses of a concave mirror. Have you seen solar heaters? Solar heaters are the devices that use energy from the sun to heat something. It is the most common device which uses a concave mirror for its function. We already know that the rays of light coming from an object kept at infinity will converge after reflecting from the surface of a concave mirror. Here, the sun is very far away, and hence the rays of light coming from it are parallel near the earth's surface. These parallel rays, after reflection, will be converged to a point called as focus. This focus is a very hard location in space, as all the sun's rays are concentrated at this point. If you bring a piece of paper at this point, it will quickly catch fire. Now we can use this property of concave mirrors to cook food or heat up liquids. All we need to do is that place the container on this stand which is present at or near the focus. It will heat up after some time. You can even make roti or papad on this. Where else on the world do we use these types of mirrors? We can use concave mirrors to view the objects which are very far away from us. Think about it. Yes, I'm talking about astronomical telescopes. How is a concave mirror is used in a telescope? When the parallel rays of light from the distant star enter the telescope, they follow the concave mirror which is placed in the opposite side. This concave mirror then converges all the light at a focal point. So the image of star is formed at this point in the space. The secondary mirror is then placed near the focal point. It is kept like this so that it can reflect the light towards the eyepiece. The eyepiece has a lens which then magnifies this image. This way we are able to see an enlarged image of a far off an object. This particular type of telescope is also called as Newtonian telescope, as it was Isaac Newton who first came up with this idea. Which is the lens used near the eyepiece? The lens used here is a convex lens or the converging lens. We all have seen this mirror which is found in bathrooms. Many men use it for shaving purposes and quite a few women use it for beautification. Yes, this is also a concave mirror. And it must be very obvious now as to why we use it here. Due to the enlarged image, it gives a better view of our face. One more place where concave mirrors are used is the headlights of the automobiles. And why do we use the headlights? Headlights help us to see the things in front of us in dark or dim light. And using the headlights, we would want to see the things which may be at sufficiently large distance ahead of us. So how do we achieve that? We know that when an object is kept at the focal point, the light rays from an object after reflection travel parallel to each other for a long distance. So we keep a light, say above or at near the focal point of a concave mirror. Then almost all the rays from the bulb after reflection will travel in one direction. If the same concept is used in the headlights of a car, it will give a distant view of the road ahead. This solves our purpose of viewing cars or things which are quite far away from us. However, in reality, we don't really want all the rays to be traveling parallel after reflection. That is, we also want some of the rays to travel a bit sideways. This will help us to see the vehicles coming from the other side of the road in the opposite direction. So for that purpose, we use what we call as deflectors. They deflect some of the light by smaller degrees. Okay, now let's look at a side view mirror of a car to know whether it's a concave or a convex mirror. We ask ourselves a simple question. What's the use of this mirror? This mirror helps us to see the vehicles that are far behind us. So if it was a concave mirror and the vehicle behind is sufficiently close, then the image formed will be enlarged. By close, I mean between the center of the curvature and the pole of the mirror. And its size will keep on increasing as the vehicle comes closer. Also, this is a real image which is inverted. We don't really want such a big image. Due to its bigger size, we are not able to judge the position of the car or the location of the vehicle behind. Also, it takes away all the space in the mirror, and because of this we are unable to see any other objects or vehicles. So, we cannot use a concave mirror as a side view mirror. What about a convex mirror? Yes, convex mirror can be used as side view mirrors because convex mirror never produce enlarged images. Images formed by a convex mirror are always diminished or smaller in size. And also, image formed by a convex mirror is always virtual image. That is the reason it appears to be formed behind the mirror. What is the advantage here? As the image is smaller in size, only a small portion of the convex mirror is required to view the image. Hence, we are able to see other objects and vehicles in the mirror. In fact, even far away objects are visible as tiny objects, so a convex mirror is used as side view mirror in automobiles. Where else are they used? They are used in the shops, especially in shops or supermarkets, which are huge with many commodities. Why are they used there? They are there for security reasons. As they give a wider field of view, one is able to keep an eye on the happenings in the larger area of the shop. Another place where they are used is the ATMs. Again here for security reasons.
The rules of spherical mirrors are also referred as sign conventions. This is also called as new Cartesian sign conventions. And what are those rules? Firstly, all distances parallel to the principal axis should be measured from the pole of the mirror. All distances u, v and f are measured from the pole of the mirror and not from any other part of the mirror. And the segment that is used to measure the distance should always be parallel to the principal axis. The second rule is that object is always placed on the left of the mirror. The rays of light emerging from the object should always travel from left to right. The third rule is that all distances are measured to the right of the mirror are taken as positive and the distances measured to the left of the mirror are taken as negative. For instance, we know that when an object is behind the center of curvature of a concave mirror, then the image is also formed on the same side. Both the image and the object are on the left of the mirror. Hence, both their distances are taken as negative. What about focal length? Will it be positive or negative? Principal focus is also on the left. Hence, it will be negative. And based on the second rule, we always keep the object on the left of the mirror. Hence, distance u will always be negative. What instead of concave mirror, we take a convex mirror and keep the object at finite distance to the left of it? In this case, we know that the image will be formed here. It's a virtual image. The object distance will always be negative. But since here the images are on the right, its distance v will be positive. What about focal length? For convex mirror, the principal focus lies to the left of the mirror. Hence, focal length is also positive. What is a mirror equation? Let's first draw a mirror. Should we draw a concave mirror or a convex one? Well, the mirror equation works for both, but let's start with the concave mirror. You are already familiar with all the symbols. P is pole, C is the center of curvature. It is the center of the sphere of which the reflecting surface is a part of. The midpoint of C and P is the principal focus. And finally, the line which joins all of them is the principal axis. Suppose our object is kept at C at a finite distance away from the mirror. We draw our usual diagram to get the image, which is of course a real image. So what is a mirror equation? Well, let me just write it down. 1 over f is equal to 1 over u plus 1 over v. What do these three letters symbolize? They are nothing but the distances between the points. To understand better, let's draw a tangent at point P like this. In these equations, u is the distance between the object and the mirror, so this distance will be u. It is the distance between the points A and P. Remember, the distance between two parallel lines will always be the same. So this distance is nothing but the distance between the points A and P. V is the distance between the image on the mirror. Let's name this point as G. So V is nothing but the distance between the points G and P. And F is the focal point, which is the distance between principal focus and the pole. So this distance is equal to F. Note that all the distances are measured from the pole of the mirror and not from some other point on the mirror. So from these equations, you can see that it gives us a relationship between the object's distance from the mirror, image's distance from the mirror, and the focal length. What if instead of this, I had placed an object somewhere else? It wouldn't change our formula. The equation doesn't depend on the object's position from the mirror. It is same for any position of the object. What if instead of a concave mirror, we had a convex mirror again? It wouldn't change the formula. Yes, this formula is true for all types of mirrors, convex as well concave. There are various properties of image found by spherical mirrors: the position, the size, and the nature of the image. These properties vary as the object's distance from the mirror varies. The property that we are going to discuss in this video is the size of the image. For a concave mirror, there are three possibilities for the size of the image relative to the object. Basically, the image can be enlarged, the image can be same size, or also can be diminished or smaller in size. For a convex mirror, the image is always smaller than the size unless the object touches the mirror. In that case, the image will be the same size of the object. Now, if we have to compare the size of the image with the size of the object, then we take the ratios. That is, ratio of the size of the image to the ratio of the size of the object. And this ratio is what we call as magnification. It is denoted by the letter M. In our ray diagram, the size of the object and the image are nothing but the heights of the object and the image. So M will be equal to Hi over H0. Suppose the height of the image is greater than the height of the object, this means that the image is enlarged. If the term in the numerator is greater than the term in the denominator, then their ratio will be greater than 1. What if Hi is less than H0? Now, the ratio will be less than 1, that is, image is diminished. What if they are equal? The equality implies both the object and the image are of the same size. If you notice, in all the three cases, we are assuming something for u. That is, both H0 and Hi be non-zero. But can they be 0? We know that when the object is at infinity, the image is point-sized. Image is formed at focal point, so here we take the size of the image as 0. However, theoretically we say that when the object is at infinity, the image is point-sized. But in reality, this is not a point-sized image because we cannot define infinity. The image, however small it is, has some dimensions. So in reality hi cannot be 0, it can be a really small number. For example 0.5 but never 0. We can apply the same logic for object size, therefore hi and h0 cannot be 0. Now there is a relation between the magnification of the object distance u and the image distance v. The relation is that hi over h0 is equal to negative v over u.
What can happen when a beam of light is incident on a surface of any object? When the light beam is incident on a surface of any object, a part of the light can be reflected by the object, a part of the light can be transmitted, that is, it may pass through the object and get out from the other side, and a part of the light can also be absorbed by the object. The amount of light reflected, absorbed or transmitted depends on the material that the object is made up of. If an object is opaque, then it will absorb or reflect most of the light back. If it is transparent, more light will be transmitted. Can you think of examples for these two? The surface of mirror is shiny and opaque and most of the light rays are reflected from it. On the other hand, glass is an example of a transparent object. It will transmit most of the light. So what is refraction of light? It is nothing but simply the bending of light when it travels from one medium to another. Yes, if this is the incident at this angle, then it goes through at another angle. Now this is not the exact definition as there are a few technicalities involved. Consider a transparent object kept here, say a glass slab. Suppose light is traveling through air is incident obliquely on the surface of the glass. What do I mean when I say obliquely? It means slant. It implies that the incident ray is neither parallel nor at a right angle to the specified line. Now this light will bend at the boundary of two media. Here the two media are air and glass. This bending of light at the boundary of two media is what we call refraction of light. What are these two mediums called? The medium from which the light is incident is called the incident medium, and the medium where refraction occurs is called a refractive medium. Similarly, here as well, the light is traveling from one medium to another medium. It's glass to air. And here also, it is incident at an angle. Since we know that a transparent media, light bends at this boundary and travels through air. So light refracts at these 2 points. Let us draw a line perpendicular to the surface at this point of incidence. This line is also called as a normal. What is this angle called? It's called the angle of incidence and is denoted by the letter I. It is an angle made by the incident ray with the normal. And this is the angle made by the reflected ray with the normal. It is called as the angle of refraction R. What happens when light is incident on the surface of a transparent object? Consider a glass slab and suppose a narrow beam of light is incident on one side. The beam of light partially reflects, partially refracts, and even partially absorbed by the object. We have already discussed the laws of reflection. The first one says that the light ray which is incident is reflected in such a way that angle of incident and the angle of reflection are equal. And the second one says that the incident ray, reflected ray and the normal all lie in the same plane. Just like for reflection, there are laws for refraction. What is refraction? Refraction is a change in the direction of light as it passes across the boundary separating two media caused by its change in speed. If the refractive medium is optically denser to compare to the incident medium, then the refracted ray will bend towards the normal. If it is optically rarer, it will bend away from the normal. Note that if the light is incident obliquely to the surface, then the incident light is perpendicular to the surface and it does not change its direction. There are two laws of refraction. The first one is same as the second law of reflection. Consider a light traveling from some medium 1 to another medium 2. which is optically denser than medium 1. So its speed in medium 2 decreases and bends towards the normal. The first law of refraction says that the incident ray, refracted ray and the normal at the point of incidence all lie in the same plane. It means that if I were to draw this on a piece of paper, they all will be on the plane of paper and not out of the paper. What about the second law? The second law is also called as Snell's law of refraction. Snell's law gives us the relation between incident and refraction angles and the refractive indexes of mediums. What is the refractive index of a medium? It is the extent to which refractive medium increases or decreases the speed of light.
A lens is nothing but a transparent material bounded by two surfaces. One of these surfaces is spherical and the other one can be either spherical or plane. Although there are different types of lenses, we only study about two types of lenses, which are called as biconvex and biconcave lenses. Each of these has two spherical surfaces. Hence, the name bi is used. In a biconvex lens, the two spherical surfaces are curved outwards, and in a biconcave lens, the two spherical surfaces are curved inwards. Another way of distinguishing these lenses is that biconvex is thicker at the center and thinner at the edges, whereas biconcave is thicker at the edge and thinner at the center. Why do we use lenses? We use the lens to diffract the light. The lens either converges or diverges the light. Do you know how the light is refracted? Consider a convex lens. Suppose a ray of light is incident on it at an angle. We know that when a ray of light propagates through a different medium, it bends. This is due to the change of speed of light between the two mediums. The degree of the bending depends upon the incident medium. Suppose the light enters from air, and since lens is made up of glass, speed of the light decreases and the light bends towards the normal. When the ray enters the air back from the glass, the ray bends again, but this time it is away from the normal. As air is rarer than glass, speed of the light in air increases and the light bends away from the normal. Here we have considered a single ray, but in reality there are many rays, and all of these rays after striking at the lens gets refracted in the same way, and we see that all the rays meet at a common point. The ray of light entering convex lens after refraction converges at a single point, and that point the image is formed. Hence, it is called as a converging lens. Similarly, a concave lens diverges the rays and hence is called as a diverging lens.